So let's continue from where we left over last time. So just to remind you, let me actually run some the same scripts we ran last time. So we ran the Euler schemes and we plotted, we did a log-log plot of the number of time steps we used in solving the Euler's formula, and the y-axis is how much error do we get at the end, right? And we run the midpoint, and if we hold on and perform a similar log-log plot, we can see that the midpoint scheme converges second order. It has a nicer, a steeper descent. So as you increase the number of grid points, the error decreases faster. And we also derived a third order scheme. And if we plot the error versus the grid points, we see the error skyrockets to some ridiculous values, even goes to infinity for a larger number of time steps, right? So, and we resolved the reason for this last lecture by doing what? Do you remember what did we do to figure out why it doesn't give us a nice solution? Yes?
When the eigenvalues magnitude is greater than 1.
Yes, eigenvalues. So we looked at the equation, we looked at the scheme we derived, and we applied the scheme to solving an even simpler equation, du dt equal to what? 0. Okay, we were solving the equation du over dt equal to 0 and applied the scheme we derived on it. And we find out that, okay, when we start the solution with a perfect value, we get the right solution. But if we perturb the initial solution just by a little bit, 10 to the minus 300, then we start getting crazy oscillations. The oscillations, it starts from 10 to the minus 300, it goes to 10 to the minus 200, 10 to the minus 100, order 1, and it goes up to infinity pretty fast. So basically the scheme is not able to solve the equation du dt equal to 0. And the reason it is not able to solve the equation is because if we apply the scheme to du dt equal to 0, the scheme is unstable in its eigenvalues. Okay, and let me just to remind you the analysis, because we'll be doing actually something similar this lecture. We will the scheme, if we apply it to solving the equation du dt equal to 0, the scheme we get would be u at time step k plus 1 would be equal to, somebody remember what we get? Let's actually look at the code to see what we have, okay? If we look at the third order scheme code, basically we see that our u is equal to minus 1.5 times is equal to minus 1.5 times uk, okay, and plus 3 times uk minus 1, and minus half times uk minus 2. So in order to perform eigenvalue analysis, we rewrote this formula into something else. We rewrote this formula into a matrix form, right? We wrote the formula like this. We wrote u of k plus 1, u of k, and u of k minus 1 is equal to certain matrix times the same 3 values, but shifted by 1 in its index. So uk, uk minus 1, and uk minus 2. The reason we write it differently is that if we write it like this, we have transformed a iteration that depends on the previous 3 steps into a iteration that only depends on the previous 1 step, right? Although by introducing more values, more state variables. That's actually a pretty commonly used trick. If we write it like this, we can fill in the matrix with the coefficients we have, and 1 and 1, right? Wherever I leave blank means 0. So we performed the eigenvalue analysis to this matrix and found an eigenvalue that is minus 2 point something.